We begin our journey with a story both improbable and real, a story whispered in observatories and quietly debated in scientific papers. They call it the planet that shouldn't exist. It is a world so far from its star, so heavy, and so old that it breaks nearly every rule our models of planet formation have taught us. The first clues appeared years ago, buried in faint data from a telescope scanning a dim star system thousands of light years away. At first, astronomers didn't believe it. The numbers suggested an object of immense mass orbiting its star at a distance so great that standard models said it couldn't have formed there. Worlds form in protoplanetary disks, swirling clouds of dust and gas, and the heavier a planet, the closer it tends to form to the star. Gas giants like Jupiter are born in regions rich in material, usually not far from the warmth and pull of their parent sun. But this world, if it existed, lived far beyond that nursery, in the cold darkness where starlight was a faint memory. In those distant zones, dust is too sparse, collisions too rare to build such a massive body in any reasonable time scale. And yet there it was, or so the data hinted. For years it remained an odd statistical blip in the records, something most researchers quietly ignored. But as the evidence grew, ignoring it became impossible. More telescopes turned toward that dim star, each adding detail to the puzzle. The planet was confirmed, real, massive, and impossibly far from home. A planet that simply should not exist, and yet it does, defying the rules of cosmic creation we thought we understood. Once astronomers accepted that this planet was real, the first question was simple. How could it have formed at all? The prevailing theory of planetary formation, the core accretion model, could not account for such a world. In that model, small grains of dust stick together over millions of years, building into rocky planetesimals. These, in turn, merge into larger bodies, eventually becoming massive enough to gather thick atmospheres of gas. But that process depends heavily on proximity to the star. Where the disk is dense with building material, farther out, the density drops, and time stretches beyond the lifespan of the disk itself. That means giant planets simply can't grow in the frozen outskirts, at least not through normal means. Some scientists suggested it could have formed closer in and then migrated outward, perhaps after a gravitational encounter with another massive planet. But this idea raised its own problems. Moving something so large to such a distant, stable orbit without ejecting it entirely from the system is exceedingly rare. Others considered whether the planet might not have formed here at all. Perhaps it was captured, a rogue wandering the galaxy until a star's gravity ensnared it. That too is unlikely, requiring a precise set of conditions and a slowing mechanism to prevent escape. The planet's atmosphere further deepened the mystery. Spectroscopic analysis showed heavy elements in proportions unusual for its location, suggesting a complex history of formation and migration. It was as if this world carried the fingerprints of multiple cosmic environments, none of which entirely fit the picture. Each observation stripped away simple answers, leaving behind a growing sense of. In the quiet corridors of research centers, the murmurs began. This planet might force us to rewrite the story of how worlds are born. To understand just how strange this planet is, we need to place it in its cosmic neighborhood. Its parent star is a middle-aged, sun-like star. Not particularly remarkable. What makes it remarkable is its distance from the planet. Hundreds of astronomical units, hundreds of times the Earth-Sun distance. At that range, sunlight is so faint, the daytime on the planet would be dimmer than Earth's full moon. The temperatures hover near absolute zero, cold enough to freeze most gases solid. This is not the kind of place we expect to find a gas giant, much less one with such mass and complexity. Imagine trying to build a skyscraper in the middle of an empty desert, where bricks arrive one grain of sand at a time. That's the scale of difficulty in forming such a planet so far from the star. And yet, when telescopes measured its orbit, they found it to be astonishingly stable. No sign of the elongated path you'd expect from a world flung outward by a chaotic encounter. Even more puzzling were signs of faint heat emissions from its atmosphere, hinting at internal energy sources. These could be leftover heat from formation, slow radioactive decay in its core, or even tidal heating from unseen moons or past interactions. The heat, small as it is, defies the extreme cold of its environment, creating a temperature profile that doesn't quite match theoretical expectations. Its atmosphere, rich in methane and hydrogen, glows faintly in infrared, a quiet beacon in the dark. Astronomers realized that studying it could reveal not only how planets form in unlikely places, but also how planetary systems evolve over billions of years. And quietly, they also wondered, if such a planet exists, how many others like it are still hidden in the shadows of space? One of the most intriguing ideas about this planet's origin comes from the theory of stellar nurseries. Stars are born in clusters, surrounded by hundreds or thousands of siblings. In such crowded environments, young planets could be stolen from one system and adopted into another. The early years of a star's life are chaotic. Disks collide, stars pass dangerously close, and gravitational forces toss objects around like debris in a storm. It's possible this planet began its life orbiting a completely different star, only to be pulled away during one of these close encounters. Over millions of years, its new host star's gravity might have captured it into the wide, distant orbit we see today. This would explain some of its unusual atmospheric composition, a mix of elements that suggest it formed in a different chemical environment. But it still leaves questions. Why is the orbit so perfectly circular? Capture events usually produce elongated orbits, slowly settling over immense timescales. And if the planet was captured, why don't we see more evidence of other captured bodies in the system? As data piled up, computer simulations tried to recreate its history, but every plausible scenario required an improbable chain of events. It was a cosmic riddle where every answer spawned new mystery. This is why scientists love such discoveries. They challenge the boundaries of our understanding, forcing us to question the assumptions baked into our models. In the grand story of the cosmos, anomalies like this are precious. They remind us that the universe is not bound by our rules. We are bound by its reality. And somewhere, far from our own sun, this lonely giant continues its silent orbit, carrying with it a story written across billions of years of cosmic history. The next major breakthrough came from analyzing the faint light reflected from the planet's atmosphere. Using advanced spectrographs, astronomers could split this light into its component wavelengths, revealing the chemical fingerprints hidden within. What they found was perplexing. Traces of ammonia ice, water vapor, and complex hydrocarbons, all layered in a way that suggested a turbulent past. Ammonia ice, in particular, hinted at extremely low temperatures during formation, colder than the environment the planet occupies now. That raised an intriguing possibility. Perhaps this planet formed even farther out in space before migrating inward to its current location, but migration from beyond its present orbit would require forces beyond a simple gravitational. The idea of a passing star disturbing the system became a stronger contender. A star skimming past in the early days of the system could have altered the planet's orbit, pulling it slightly inward and locking it into stability. If this were true, the planet's history might span multiple stellar neighborhoods. It could carry the chemical memories of regions of space we could never visit. This makes it a kind of time capsule, preserving conditions from an era when the sun itself was young. For planetary scientists, such a world is like a Rosetta Stone, offering clues not only to how planets form, but to the larger question of how entire solar systems evolve. The fact that it still exists without being ejected into interstellar space means that some delicate balance has been maintained for billions of years. Every observation deepened the planet's mystery and widened its implications. If one such planet can survive against all odds, then perhaps the galaxy is full of hidden giants waiting in the cold darkness for our instruments to find them. While its orbit remains remarkably stable, the planet itself is anything but static. Deep within its atmosphere, powerful jet streams move gases in patterns that seem almost choreographed. Observations show that these winds can reach hundreds of kilometers per hour, driven not by sunlight but by internal heat. This hints at a large and still warm core, a relic of its formation billions of years ago. If the planet truly formed in deep space, then its heat retention over such timescales is impressive, suggesting a dense composition and possibly a layered structure like Jupiter's, but with unique differences. Beneath the thick clouds, layers of metallic hydrogen might swirl around the core, generating magnetic fields far stronger than Earth's. These magnetic fields could trap particles and create faint auroras, invisible to human eyes, but glowing in the infrared. Theoretical models even suggest that such magnetic activity could help the planet hold on to its atmosphere despite the constant pull of the cold vacuum. And then there is the possibility of moons. Some gravitational anomalies in the planet's motion hint at the presence of one or more large satellites. If such moons exist, they could be fascinating in their own right, icy worlds warmed by tidal forces with subsurface oceans hidden beneath kilometers of frozen crust. These moons could even harbor the chemical building blocks of life, preserved in isolation for eons. The thought that such environments might exist so far from any star challenges the traditional view that life requires warmth from sunlight. In this distant, frozen realm, it is heat from the planet itself that could make life possible, even if only in its most primitive forms. The search for these moons became a priority for astronomers. Detecting them at such distance is incredibly challenging, requiring the most sensitive instruments on Earth and in orbit. Even a small wobble in the planet's light curve could indicate a moon passing in front of it. But so far, the data remains inconclusive. Still, the potential rewards drive the effort forward. If confirmed, these moons could serve as laboratories for understanding habitability in the most extreme conditions imaginable. They would also shed light on the planet's origin. Captured planets often have irregular moons, while planets formed in place tend to have more orderly systems. In the meantime, attention has turned to the planet's interaction with its star's outer debris belt. Observations suggest that the planet's gravity may be shaping the belt's structure, creating subtle gaps and arcs similar to those seen in Saturn's ring. This is another clue to its mass and gravitational influence, and a reminder that even from hundreds of astronomical units away, a planet can still sculpt its surroundings. It is a strange irony. This world, bathed in darkness and almost unimaginably cold, still exerts a quiet power over its environment. For scientists, this is a reminder that in the cosmos, presence is not always about brightness or proximity. Sometimes, it is the hidden giants, the ones you can barely see, that shape the story of a system. And as data continues to trickle in, piece by piece, the planet's portrait grows sharper, yet no less mysterious. Every answer leads to new questions, and the deeper we look, the more we feel the limits of what we know. The planet's distance from its star is so extreme that the star itself would appear only as a bright point in its dark sky, far dimmer than our sun appears from Earth. Yet the planet's surface, or rather its upper cloud layers, is never truly still. In the faint starlight, particles of frozen methane and ammonia drift slowly downwards, forming hazy, glowing bands. Scientists theorize that storms here could last for centuries, locked in slow, swirling patterns dictated by deep-seated convection currents. What truly intrigues researchers, however, is how the planet could have retained such an atmosphere without being stripped bare by cosmic rays and stellar wind during its history. A strong magnetic field could explain it, but that requires a specific internal composition and rotation rate, both of which are still speculative. Computer models suggest that the planet may have undergone several phase shifts in its lifetime, where its interior structure changed as pressures and temperatures deep within evolved. These shifts could have generated bursts of magnetic activity, creating temporary shields at critical moments in its past. Without such events, the planet might have lost its atmosphere entirely, leaving only a frozen, airless husk. This idea has fascinating implications. Perhaps many planets form in harsh environments, but only those with dynamic interiors survive to old age. The planet then is a survivor, a cosmic elder, with a story of endurance written into its clouds and storm. Its continued existence challenges our expectations about the fragility of world. Astronomers studying the planet's chemical makeup were particularly fascinated by the unexpected presence of organic molecules in its upper atmosphere. These are not signs of life, but rather complex carbon-based compounds that can form in certain temperature and pressure conditions. Their presence here is unusual because they normally break down quickly under radiation, yet they appear to be stable in this environment. This stability could be due to the planet's position in a region of space with relatively low background radiation, or it might result from the protective influence of its magnetic field. Another possibility is that these molecules are constantly replenished by chemical processes in the atmosphere itself, or even by impacts from icy comets carrying fresh material. If the latter is true, the planet may be part of a wider network of bodies exchanging matter over immense timescales. Such interactions could help explain the diversity of compositions we see in exoplanets across the galaxy. For those looking for parallels to early Earth, this is intriguing. Some theories of life's origins propose that organic molecules arrived here via cometary impacts. While the planet's distance and cold climate make the emergence of complex life unlikely, the building blocks are present, and they have endured for billions of years. It is as if the universe is reminding us that the ingredients for life are scattered everywhere, even in the most improbable corners. Long-term monitoring has revealed that the planet's orbit is ever so slightly eccentric, not perfectly circular, but stretched into an ellipse. This subtle elongation means that over the course of its centuries-long year, the planet experiences tiny variations in temperature. While insignificant by Earth standards, these fluctuations could have major impacts on atmospheric circulation over millennia. There's also the tantalizing suggestion that this eccentricity is maintained by the gravitational influence of another unseen giant in the system, possibly a smaller ice giant or even a brown dwarf. If such a companion exists, finding it could answer many of the remaining questions about the planet's origin. For instance, a brown dwarf companion could have disrupted the early protoplanetary disk, scattering material and leading to the formation of a planet in such an improbable location. This scenario would tie the planet's existence to a history of cosmic violence, gravitational battles between massive bodies that left scars on the system's architecture. It also reminds scientists that planetary systems are not static. They evolve through chaotic events, collisions, and migrations. The planet we see now is the result of those ancient upheavals, shaped into its current form by forces far, far in its own gravity. When researchers modeled the planet's formation under various scenarios, they kept running into a paradox. The amount of solid material available at its current location should have been far too small to form such a massive world. Even over hundreds of millions of years, the thin gas and dust in that region would not have been enough to create a core large enough to hold on to its atmosphere. This suggests the planet must have formed elsewhere in a denser, richer part of the disk and then migrated outward. But planetary migration on such a scale is difficult to explain without destabilizing the entire system. One theory suggests that the planet was part of a resonant orbital chain early in its history, moving in lockstep with other planets until some event, perhaps a passing star or the ejection of another planet, broke the chain. This would have flung the planet outward into its current lonely position. The energy involved in such a migration is immense, and the fact that the planet survived intact makes it all the more remarkable. It is a testament to the resilience of planetary structures and perhaps a hint that the galaxy holds many other wanderers like it, hidden in the shadows. In a sense, studying the planet is like reading a mystery novel where key pages are missing. Every new observation offers a tantalizing clue, but also raises fresh questions. We know its composition is unusual, its orbit improbable, and its history violent, yet we still don't fully understand why it exists at all. This uncertainty is not a source of frustration for scientists, it is a source of wonder. The planet is a reminder that the universe does not conform to our neat models and predictions. It creates worlds that defy our logic, that exist outside the boundaries of what we think is possible. And in doing so, it pushes us to expand those boundaries. For those who gaze at it through telescopes, the planet is a beacon in the dark, not because it shines brightly, but because it embodies the unknown. It tells us that there is still so much we have not seen, so much we have not understood. In the quiet of the observatory, with the hum of instruments in the background, astronomers look at this distant, cold world and know that it will keep its secrets a little longer, and that is exactly what makes it so compelling. One of the more unexpected findings came from a rare planetary occultation when the planet passed directly in front of a distant background star. This event allowed astronomers to measure its atmosphere with extraordinary precision as the starlight filtered through its gaseous layers. The data revealed a thin haze of exotic compounds, including trace amounts of hydrogen cyanide, phosphine, and acetylene. While none of these point directly to life, they do tell a story of intense and complex chemistry unfolding in the planet's upper reaches. On Earth, some of these compounds are produced by living organisms, but here they are likely the result of high-energy reactions driven by ultraviolet light from the planet's distant star, or by electrical discharges in the atmosphere. The presence of phosphine is especially intriguing, as it requires energy to form and breaks down rapidly without replenishment. That means there must be ongoing processes keeping it present, and scientists are now racing to determine what those could be. In the dim light of the planet's skies, lightning may be flashing unseen in colossal storm systems, their energy fueling the chemistry that keeps the atmosphere dynamic. The deeper layers of the planet remain beyond our direct observation, but simulations suggest a turbulent, superheated mantle beneath a thick, icy shell. Temperatures here may be thousands of degrees Celsius, enough to keep water in a strange, high-pressure form known as superionic ice, a state where water molecules are locked in place like a solid, yet their hydrogen atoms move freely like a fluid. This exotic phase is thought to be highly conductive, and if it exists here, it could be responsible for the strong magnetic field hypothesized earlier. Such a field would not only shield the atmosphere from solar wind, but could also create breathtaking auroras shimmering across the planet's poles in colors we can only imagine. These auroras might even be visible from space as faint glows, silent signals of the powerful forces at work deep below the surface. Studying such a world offers a rare glimpse into the extremes of planetary physics, conditions so alien that they challenge even our most advanced models. Perhaps the most haunting aspect of the planet is its isolation. It orbits far from its star, far from the warmth and light that give most worlds their vitality. Its year spans centuries, its seasons barely perceptible, yet it endures, a slow-moving sentinel in the deep cold. For billions of years it has circled its star in patient silence, untouched by the chaos that often reshapes planetary systems. To imagine standing on its cloud tops, if that were possible, would be to look out over an endless expanse of darkness with a faint star hanging like a lantern on a distant horizon. The sky would be alive with other stars far brighter than the one it calls its own. In that solitude lies a strange beauty, a reminder that not all planets bask in sunlight. Some live their entire lives in the shadows, holding their secrets until someone or something comes to find them. Researchers are increasingly turning to next-generation telescopes to unlock the planet's mysteries. Instruments like the James Webb Space Telescope and future observatories promise to detect subtle shifts in its spectral lines, revealing not only atmospheric composition, but also hints of surface or cloud dynamics. Even slight changes in reflected light could indicate seasonal weather patterns, circulation shifts, or large-scale storms. There is even hope that gravitational microlensing, a technique where the planet's gravity bends the light of a background star, might allow for a more precise measurement of its mass. These technologies are slowly bringing the distant world into sharper focus, each pixel of data a step toward understanding how such an improbable planet came to be. Yet, every advance also serves as a humbling reminder: the universe's capacity for surprise is far greater than our ability to anticipate it. The planet's discovery has sparked debates that go beyond astronomy. Philosophers and scientists alike have pondered what its existence says about our place in the cosmos. If such an unlikely world can form and survive, then perhaps the universe is filled with countless other impossible planets, each with their own improbable histories. This idea forces us to question the very assumptions we make when searching for habitable worlds. Are we too focused on Earth-like conditions, overlooking stranger, more diverse possibilities for life? The planet may be inhospitable to us, but it could be perfectly suited to life forms beyond our current imagination. This shift in thinking could reshape how we explore the galaxy, encouraging a broader, more open-ended search. The lesson here is simple but profound. The universe is not limited by what we think is possible, and neither should our curiosity. One of the emerging theories about the planet's strange existence involves a violent past. Some researchers suggest it may be the remnant core of a gas giant stripped of its thick atmosphere by an ancient cataclysm. Billions of years ago, it could have orbited much closer to its star, bathing in intense radiation. Over time, tidal interactions or gravitational encounters with another massive object might have flung it outward to its current frozen orbit. In the process, much of its gaseous envelope would have been lost, leaving behind a dense, metallic and icy body, the skeleton of a once mighty world. This scenario could explain some of its unusual density and composition. It also hints at the turbulent dynamics that may be common in planetary systems, where close encounters and cosmic collisions are not rare but part of the natural order. If this theory holds, the planet is not just a curiosity, it's a survivor, carrying scars from a chaotic youth into the quiet present. From a scientific perspective, the planet challenges what's called the planetary formation bias. We often base our understanding of planets on what we've observed in our own solar system. This is natural. It's the only example we can explore in detail. But the existence of this world forces us to expand that view, to consider that nature may produce stable planets under conditions we once considered impossible. This is similar to the revolution in astronomy when hot Jupiters were first discovered. Giant planets orbiting extremely close to their stars, something models initially said couldn't happen. Just as those discoveries rewrote textbooks, this one is quietly doing the same. It's a humbling reminder that the universe rarely follows our rules. It operates on its own logic, shaped by forces and interactions that we may not yet fully understand. One of the most captivating aspects of studying this planet is how it unites multiple scientific disciplines. Astronomers measure its light curves, spectroscopists analyze its atmosphere, geophysicists model its interior, and even chemists play a role in understanding its complex reactions. The data streams from different corners of science merge into a single, interconnected puzzle. And while the planet may be far beyond the reach of spacecraft for centuries to come, the collaboration it inspires is happening here and now. It is a testament to how discovery doesn't just expand our view of the universe, it also brings people together. Each new piece of information about this improbable world is another brushstroke in a cosmic painting, one that is still far from finished. For future explorers, the planet poses a question of ambition. Could humanity ever send a probe so far? The distances are staggering, and even our fastest spacecraft today would take thousands of years to arrive. But in imagining such a mission, scientists are already pushing the boundaries of propulsion technology, thinking about light sails, nuclear drives, and other innovations that could one day make interstellar exploration possible. In this way, the planet becomes a beacon, not just of scientific curiosity, but of technological aspiration. It calls to us from across the void, daring us to bridge the gulf. Even if no probe ever arrives, the attempt itself could lead to breakthroughs that change how we travel, how we communicate, and how we see our place in the cosmos. Ultimately, the planet that shouldn't exist is less a mystery to be solved and more a mirror reflecting our own limitations and our potential. It teaches us that our models are only as good as the data we have, and that every unexpected discovery is a chance to improve them. It reminds us that the universe is a place of staggering diversity, where even the rarest conditions can give rise to something enduring, and perhaps most importantly, it offers a quiet truth. The cosmos is under no obligation to make sense to us. We must be the ones to rise to the challenge, to stretch our understanding until it can hold the wonders we find. In the darkness where it orbits, this planet spins silently, keeping its secrets. For now, but secrets, as history shows, never stay hidden forever. When astronomers discuss the planet that shouldn't exist, they often return to a fundamental question: how do we define what is possible in the universe? The discovery of exoplanets over the last few decades has repeatedly shown us that nature seems to experiment in ways our models never predicted. This world fits neatly into that tradition of surprises. What makes it even more remarkable is that it's not simply an outlier in one category. Its size, density, orbit, and age all challenge standard expectations at once. It's as if the universe decided to create a checklist of planetary impossibilities and then quietly ticked every box in the same object. The result is a silent testament to the complexity of cosmic evolution. Every time we think we've seen the limits, the sky produces something that pushes them further. The planet becomes a case study in intellectual humility, a reminder that impossible often just means not yet understood. This is why so many scientists, even those far outside planetary science, are watching that study closely. It's not just about learning how this one planet formed, it's about learning how to expand our imagination in a way that still respects the rigor of evidence. Some research teams have explored the possibility that the planet might not have formed in its current system at all. Instead, it could be a rogue planet captured by its present star after drifting through interstellar space. If true, that would make it a cosmic refugee, a survivor of some violent ejection from its birthplace. Rogue planets are thought to be surprisingly common, perhaps even outnumbering the stars in our galaxy. Most wander alone in the cold and dark, forever unbound to any sun. But on rare occasions, gravitational dynamics can bring such a wanderer into the orbit of a star, adopting it into a new family. This scenario could explain several of the planet's unusual features, particularly if it formed around a completely different type of star under conditions that no longer match its current environment. If this theory is correct, the planet's strange properties are not anomalies at all. They are simply relics of a different chapter in its history. Studying it then would be like studying a fossil from another world, preserved and displayed under the light of an alien sun. Another striking feature of the planet is its orbital stability. Despite being in what astronomers would consider a dynamically challenging position, it has maintained a nearly constant orbit for billions of years. Simulations suggest that slight differences in its initial conditions could have led to dramatic instability, sending it right into another planet or ejecting it entirely from the system. That it didn't happen speaks to a delicate gravitational balance, one that seems improbable when modeled but clearly exists in reality. This balance could be the result of subtle resonances with other bodies in the system, invisible harmonies that keep everything in place. It's almost as if the planet's position is a note in a cosmic chord, one that would sound different, perhaps even discordant, if moved. This analogy isn't just poetic. It reflects a genuine physical principle. Orbital resonances can stabilize otherwise precarious arrangements. If this is what's happening here, the planet is part of a gravitational symphony, playing its role in a composition billions of years in the making. The search for life on the planet is a quieter question, overshadowed by the puzzle of its existence. Given its conditions, potentially extreme temperatures, unusual atmosphere, and uncertain chemical balance, most scientists are skeptical that it could host life as we know it. But skepticism doesn't mean dismissal. Extremophiles on Earth have repeatedly shown that life can thrive in places we once thought sterile. Deep in ice sheets, within boiling hot springs, even inside rocks miles beneath the surface. If life does exist here, it would likely be microbial, adapted to the planet's peculiar chemistry and perhaps dependent on energy sources, unlike those that power ecosystems on Earth. Detecting such life from across the light years would be extraordinarily challenging, but not impossible. Future telescopes capable of resolving the planet's atmosphere in fine detail might catch the chemical fingerprints of biology, a thin whisper of oxygen, methane, or other molecules in ratios that defy purely geological explanation. For now, it remains an open question, one that hovers like a faint light on the horizon of possibility. One of the more imaginative hypotheses is that the planet may possess a layered internal structure unlike anything we've seen before. While Earth has a metallic core, a rocky mantle, and a thin crust, this world could have alternating layers of exotic ice, high-pressure metals, and crystalline forms of elements that do not exist naturally on our planet. At the immense pressures deep within such a body, materials can behave in strange ways. Water can become ice that is denser than rock, iron can flow like a liquid, and carbon can crystallize into diamond-like phases. The existence of these structures could explain anomalies in the planet's mass distribution detected through subtle shifts in its gravitational pull. If we could somehow peer into its depths, we might find a geological record not only of its own formation, but of the extreme physics at play inside worlds that live on the edge of possibility. The planet has also become a point of interest for those studying planetary atmospheres. Even if its atmosphere is thin, the chemical composition could reveal key insights into its history. For example, an abundance of heavy noble gases like xenon might indicate that it once had a much thicker envelope lost over time through thermal escape or impact events. On the other hand, an unexpected surplus of lighter molecules could suggest recent outgassing from the interior, hinting at ongoing geological activity. Studying atmospheres at such distances is difficult. Astronomers rely on techniques like transmission spectroscopy, capturing starlight as it passes through the planet's atmosphere during transit. Every measurement is a challenge. with signals buried in noise. Yet each faint absorption line in the spectrum is like a letter in a cosmic language, slowly spelling out the story of how this improbable world came to be. In cultural terms, the planet has also sparked interest far beyond the scientific community. It has appeared in science fiction novels, inspired digital art, and been the subject of documentaries that capture the public's imagination. There is something inherently compelling about a world that seems to break the rules. It invites comparisons to mythic lands from ancient stories, places at the edge of the known world where the ordinary order of nature. These parallels are not accidental. Human beings have always been drawn to the mysterious, to the things that lie just beyond the map. In that sense, the planet is a modern equivalent of the old phrase, "Here be dragon." It is a place we cannot yet reach, but one that calls to us nonetheless, an enduring symbol of the unexplored. As research continues, the planet is teaching us something essential about science itself. The point is not merely to explain what we already expect, but to investigate the unexpected with the same rigor and curiosity. This world is a stress test for our theories, a challenge to refine them until they can account for not only the average case, but the extraordinary, and in doing so, we move a little closer to understanding the full scope of what the universe can create. Whether the planet ultimately proves to be a captured rogue, a stripped giant, or something even stranger, it will have served its purpose to expand the boundaries of our knowledge. And perhaps one day when our descendants look up at the night sky from the surface of another world, they will see this improbable planet shining faintly among the stars and remember that it was once a mystery that pushed humanity to dream bigger. Among the many puzzles this planet presents, one of the most perplexing is its relationship with its star. Stars exert a profound influence on their planets, shaping their climates, atmospheric chemistry, and even internal activity through tidal forces. Yet, the host star here appears almost indifferent to its strange companion. Spectroscopic studies show that the star is remarkably stable with minimal variability that could disturb planetary conditions. This stability makes the planet's anomalies even harder to explain because there is no evidence of stellar flares, mass ejections, or chaotic orbital history that might have transformed it dramatically. In most cases where planets break the rules, we find a turbulent past with their stars. Yet here the partnership seems calm, ancient, and uneventful. This raises questions about whether the planet's oddities were baked in from birth, the result of a highly unusual formation scenario, rather than something that evolved later. Understanding that distinction could help scientists separate anomalies caused by external events from those caused by fundamental planetary processes. One method astronomers use to probe a planet's secrets is by studying its transit timing variations, slight changes in the exact moment it crosses its star from our perspective. These variations can reveal the gravitational tug of other unseen bodies in the system, such as additional planets or large moons. In this case, the data hints at something intriguing, a subtle but consistent variation that could point to the presence of an unusually massive moon. If true, this would add another layer of impossibility, as such large moons are thought to form only in specific scenarios, like giant impacts or co-formation within a dense disk. This moon, if confirmed, might have its own strange composition, shaped by the same improbable forces that created its parent world. The idea of a double anomaly, a planet and moon both defying expectations, is something planetary scientists find almost irresistible, because it forces them to expand not just one model, but multiple interconnected ones. Gravity is a constant across the universe, but its local effects can vary dramatically depending on a planet's mass and size. On this world, surface gravity is estimated to be far higher than Earth, yet not as extreme as that of a gas giant. This in-between range would create a profoundly different experience for any hypothetical visitors. Walking would feel heavy and effortful, while jumps would be short and exhausting. Over evolutionary timescales, any native life, if it exists, would likely evolve with thick, powerful muscles and strong bone structures. The planet's higher gravity might also influence weather patterns, causing denser atmospheres and slower, more crushing winds. For spacecraft, the increased escape velocity would pose a significant engineering challenge, making launches far more energy-intensive than on Earth. All of these factors mean that the physical environment here is not just unusual, but deeply inhospitable for humans, reinforcing the idea that this planet exists in a category of its own. The composition of the planet's crust is another frontier of speculation. Remote sensing suggests the presence of elements rare on Earth's surface, potentially including high concentrations of titanium, vanadium, and other refractory metals. These could have condensed early in the planet's history from a superheated disk of material unusually rich in such elements. Alternatively, the abundance might be the result of a catastrophic event. Perhaps the planet was once the metallic core of a much larger body whose outer layers were stripped away by collisions or tidal forces. If so, what we see today would be the exposed skeleton of a former world, its mineral wealth a byproduct of its violent past. Such a crust would not only be geologically fascinating, but could also influence the planet's color and reflectivity, subtly altering the spectrum of light it reflects and affecting how we detect and characterize it from afar. Climate models of the planet have proven especially difficult. Without precise measurements of its atmosphere, scientists must rely on simulations that incorporate a wide range of possible conditions. Some scenarios predict a dry, barren surface scorched by its star. Others suggest a cloudy, high-pressure environment where sunlight barely reaches the ground. There are even exotic models in which the surface is hidden beneath a deep global ocean, heated from below by internal geothermal activity. In such a case, the planet might resemble a scaled-up version of Europa or Enceladus, with a dark, alien ocean teeming with chemical activity. While we have no direct evidence for any of these outcomes, the sheer diversity, plausible climates, makes the planet a natural laboratory for testing how atmospheric chemistry, stellar radiation, and geology interact under extreme conditions. One fascinating angle in the study of this planet is the role of magnetic fields. A strong magnetic field can shield a planet's surface from harmful cosmic and stellar radiation, preserving its atmosphere over billions of years. However, if the planet's composition is as unusual as we think, its magnetic field might behave in ways unlike anything in our solar system. Perhaps it is generated not by a molten iron core, but by an entirely different conductive layer. Or perhaps it is intermittent, waxing and waning over millennia. Such variability could have profound consequences for atmospheric retention and any potential biosphere. If the magnetic field is weak or absent, the planet's atmosphere might have been steadily eroded, leaving it more vulnerable and exposed. If strong, it could be a silent protector, maintaining surface conditions far more stable than expected. Either outcome would deepen the mystery of how this improbable planet survives. The question of the planet's age remains open. Current models suggest it could be older than Earth, possibly by several billion years. If so, it would have had a much longer history of internal and atmospheric evolution, potentially passing through phases that we can only guess at. It might once have been warm and temperate, or even briefly habitable, before shifting into its current state. The longevity of its orbital stability suggests that whatever changes occurred were driven internally rather than by catastrophic encounters. Understanding its age is crucial because it would tell us how long the processes that shaped it have been at work, and whether we are seeing the planet in its final form or just one stage in a much longer cycle. The planet's discovery has also revived discussions about the rare Earth hypothesis. The idea that while planets may be common, those capable of supporting complex life are exceedingly rare. This world seems to support that idea, not because it is habitable, but because it is so distinctly uninhabitable despite its superficially Earth-like characteristics. It's a reminder that the Goldilocks zone, the region where liquid water could exist, is not a guarantee of comfort or stability. Instead, countless other factors, composition, magnetic shielding, geological activity, orbital dynamics, must align just right. This planet demonstrates how easily those factors can combine in unexpected ways, producing a world that defies neat classification. Speculative theories have even ventured into the possibility that the planet's anomalies might be the remnants of artificial engineering, not by humans, of course, but by an ancient civilization long vanished. While such ideas remain firmly in the realm of the unproven, they serve as reminders that the universe may hold surprises that extend beyond purely natural processes. A planet designed for a specific purpose or altered for some unknown reason would present signatures much like those we observe here: unusual composition, improbable orbit, and unexplained stability. Most scientists caution against jumping to such conclusions, but even entertaining the thought underscores the vast range of possibilities the cosmos might contain. As our instruments grow more powerful, we will learn more about the planet that shouldn't exist, but perhaps never everything. There will always be elements hidden from us by distance, resolution limits, and the sheer complexity of nature. And maybe that's the point. This planet is a reminder that mystery has value in itself. It keeps our curiosity alive, drives technological innovation, and forces us to refine our understanding of the universe. Whether its origins are mundane or extraordinary, it has already served its purpose by expanding our sense of the possible. In a cosmos where the rules seem unbreakable, it stands as quiet proof that nature writes its own exceptions. In studying this world, astronomers have turned to computer models to simulate its birth and evolution. They feed in parameters, mass, orbit, density, composition, and then let the models run backward in time, attempting to rewind the planet's history. The results are frustrating. Most simulations either fail to produce a planet like this at all, or require highly improbable starting conditions. In one scenario, the planet forms far from its star, beyond the frost line where ices dominate, before migrating inward to its current orbit. But such migration usually leaves gravitational scars, disturbing the orbits of other bodies in the system. Here, no such scars are found. Another model suggests it may have formed after a massive collision between two protoplanets, yet the specific mix of metals and volatiles doesn't match the expected outcome of such an event. Each failed simulation deepens the enigma, pushing researchers to rethink their assumptions about planetary formation entirely. It's rare for a single discovery to challenge so many different models at once, but this planet does exactly that, quietly defying our most confident theories with its silent presence in the night sky. Among the many unusual qualities of this planet is its albedo, the fraction of light it reflects back into space. Measurements show it to be unusually high, meaning it is far more reflective than most worlds of its type. This could be due to a surface or atmospheric composition rich in bright clouds, ice, or reflective minerals. On Earth, a high albedo helps cool the planet as more sunlight is bounced back into space. On this world, the implications are complex. A reflective surface might keep temperatures lower than expected, altering weather patterns and perhaps even the planet's color when seen from afar. This reflective quality also affects how we detect and measure the planet. Many of our instruments rely on the tiny dip in starlight during a transit to determine its size. An unusually bright atmosphere can distort these readings. If the planet's surface or clouds are acting like a cosmic mirror, then our current measurements of its size, temperature, and composition may be subtly wrong, another twist in a puzzle already overflowing with. A growing area of interest is whether this planet might belong to a rare class known as super-Earth or mega-Earth. These are rocky worlds larger than our own, with much stronger gravity and potentially denser atmospheres. In some cases, such planets can hold on to heavy gases that smaller planets would lose to space. If this is the case here, it might explain some of its atmospheric mystery. Perhaps the air is thick with exotic compounds like sulfur hexafluoride or methane-rich smog, substances that would be unstable or rare on Earth. A thick, dense atmosphere would also create a very different surface environment. With crushing pressures and dim light filtering through, if life exists, it would have had to adapt to slow chemical cycles, limited sunlight, and a climate unlike anything in our solar system. In such an environment, evolution might favor low metabolism organisms, creatures that move slowly, think slowly, and live for extraordinary lengths of time. Whether such life exists is unknown, but the possibility lingers at the edge of every new observation. The possibility of rings around this planet has intrigued observers. Rings are not just the domain of gas giants like Saturn. Even smaller bodies can possess them under the right conditions. If this planet has a dense ring system, it could be the result of a captured moon that was torn apart by tidal forces or of debris left over from ancient collisions. Such rings would add to the planet's reflectivity, potentially explaining its high albedo. They would also have dramatic effects on the planet's climate and seasons, as sunlight filtering through the rings could create patterns of alternating light and shadow across its surface. From a visual standpoint, the sight of such rings would be breathtaking. Sweeping arcs of dust and ice encircling a planet that already defies categorization. Detecting these rings, however, requires precise measurements during planetary transits, looking for subtle variations in starlight before and after the planet passes. The search is ongoing, and any confirmation would be another extraordinary twist in an already baffling cosmic story.
Seismic activity is another unknown.
On Earth, quakes and volcanic eruptions are driven by plate tectonics and internal heat. On this planet, if internal heat sources are abundant, perhaps from radioactive decay or residual heat from formation, there could be intense geological activity. Volcanism might produce vast plains of basalt or towering mountains of exotic minerals. If the crust is rich in metals, eruptions might spew glittering particles into the atmosphere, contributing to its brightness. Conversely, if the planet has cooled significantly, it might be geologically dead with no active tectonics at all. A frozen, rigid crust would change the way surface features evolve, leading to ancient impact craters that remain sharp and unweathered for billions of years. Understanding this aspect is critical, because geology plays a major role in shaping the planet's atmosphere and climate, and without seismic activity, a planet can lose one of the key engines that renew its surface and maintain long-term habitability. In terms of orbital stability, this planet's path around its star is almost unnervingly perfect. Many exoplanets have slightly elliptical orbits, leading to seasonal extremes as they move closer to and farther from their suns. Here, the orbit is nearly circular, producing minimal seasonal variation. This stability might have been a factor in the planet's long-term survival, as extreme shifts in temperature can destabilize atmospheres or even destroy surface environments. How it achieved such a stable orbit is another mystery. Some theorize it formed there and never moved. Others suggest it underwent a process of gravitational shepherding by another unseen body that gradually smoothed out its path. Whatever the cause, the effect is the same. A world that travels in near-perfect harmony with its star, as if locked into a cosmic agreement that has lasted for billions of years. Atmospheric circulation patterns on this planet, if we could observe them directly, might astonish us. On Earth, winds and ocean currents distribute heat, regulating climate. On this world, depending on its rotation speed and axial tilt, the atmosphere could behave in unfamiliar ways, perhaps with gigantic, slow-moving storms that last for centuries, or jet streams that circle the globe in strange looping patterns. If the planet rotates very slowly, one side might be in permanent daylight, while the other endures endless night, creating a stark division between a scorching hemisphere and a frozen one. In such a case, the habitable zone might be a narrow twilight belt where temperatures are just right, even without life. Such patterns would be fascinating, offering a glimpse into the limitless variety of climates the universe can produce. The planet's chemical fingerprint, as revealed by spectroscopy, contains traces of compounds that are difficult to explain. Some of these may be naturally occurring minerals vaporized into the atmosphere, but others might require more exotic origins. For example, certain complex hydrocarbons are typically broken down quickly by ultraviolet radiation, yet here they persist, suggesting some process is replenishing them. This could point to ongoing geological activity, unusual atmospheric chemistry, or something even stranger. In the search for life, scientists sometimes look for biosignatures, gases that are hard to explain without biological activity. While no definitive biosignatures have been found here, the persistence of these compounds is a tantalizing hint that the planet's story may be more dynamic than we think. Cultural fascination with this planet has grown since its discovery. It has appeared in speculative fiction, art, and even music, often depicted as a hauntingly beautiful, dangerous place, a siren world calling explorers across the void. In these depictions, it is sometimes imagined as a last refuge, sometimes as a forbidden realm hiding ancient secrets. The reality, of course, is still unknown, but the way it has captured human imagination speaks volumes about our need to find meaning in the unknown. The planet has become a symbol of mystery, a reminder that even in an age of powerful telescopes and deep space probes, there are still places in the cosmos that lie far beyond our understanding. Perhaps the most remarkable thing about the planet that shouldn't exist is the way it forces collaboration to study it. Astronomers, chemists, geologists, and computer scientists must all bring their expertise together. No single discipline can unravel all its mysteries alone. This collaborative effort is mirrored in the way telescopes around the world, and even in space, work in unison, pooling data and resources. It's a quiet reminder that the universe's most profound puzzles are often too vast for any one mind or even one nation to solve. The planet's truth, whatever it may be, will be revealed only when we bring together the full range of human curiosity and ingenuity. Until then, it will remain exactly what it is now, a silent enigma orbiting its star in perfect, improbable balance. When we observe this planet through different wavelengths, visible light, infrared, ultraviolet, a richer picture begins to form. Infrared imaging, in particular, can reveal the planet's temperature profile, showing where heat is trapped or lost. These readings suggest that heat is distributed more evenly than expected for a planet at this distance from its star. On most worlds, the equator is significantly warmer than the poles, but here, the gradient is surprisingly mild. This could be due to strong atmospheric mixing, or perhaps the planet's rotation rate is just right to prevent extreme differences. If the heat balance is maintained naturally, it could help explain why the atmosphere remains stable over long timescale. On Earth, we rely on such balance to keep climate cycles predictable. On this world, it may be the same, or it could be the result of entirely alien mechanisms. Infrared studies also hint at mysterious hotspots, that don't align with expected patterns. Whether these are volcanoes, impact scars, or something stranger remains unknown, but they stand as another reason this world draws so much attention. Magnetic fields are critical in planetary science because they shield atmospheres from stellar winds. Earth's magnetic field, generated by the motion of molten iron in its core, prevents our atmosphere from being stripped away over time. On this planet, detecting such a field is challenging, but indirect evidence suggests it may have a surprisingly strong one, perhaps even stronger than Earth's. This would have major implications for atmospheric retention and potential habitability. A powerful magnetic field could also mean an active molten core, possibly with complex internal layering. This internal dynamo might be driven by different processes than those on Earth, depending on the planet's composition. If confirmed, such a strong field could help explain why the planet has maintained its atmosphere for billions of years, despite orbiting relatively close to a star. And if auroras exist there, they could be spectacular, shimmering displays of charged particles colliding with atmospheric molecules, painting the skies in colors never seen on Earth. The planet's discovery has also prompted a reevaluation of the host star itself. Stars are not static. They evolve, brighten, and change over time. If the star was significantly different in its youth, it could alter the entire history we imagine for this planet. For example, if the star was once hotter and more luminous, the planet's surface might have been far too warm for liquid water. Yet now, conditions may be cooler and more temperate. Alternatively, the star could have been dimmer in its early days, forcing the planet to survive through other means, such as greenhouse heating from its atmosphere. Understanding the star's age, variability, and chemical makeup is therefore as important as studying the planet itself. Any miscalculation in the star's history could send our planetary models in the wrong direction, much like a faulty clock throwing off an entire navigation system. In this way, the planet and its star are deeply entwined in a cosmic dance, each shaping the other's fate. One of the most perplexing questions is whether the planet has moons. Moons can reveal a great deal about a planet's past. Their size, composition, and orbits often hold clues to how the system formed. Detecting moons around distant exoplanets is notoriously difficult, but astronomers are beginning to refine techniques such as transit timing variations, TTV, where the gravitational pull of a moon slightly alters the timing of the planet's orbits. If this planet does have moons, they could be remnants of collisions, captured asteroids, or even co-formed companions. In a few scenarios, large moons can stabilize a planet's axial tilt, preventing chaotic climate swings. On Earth, our moon is believed to play such a role. If something similar is happening here, it could be one of the hidden keys to the planet's long-term stability, and if any moons are geologically active, they could add yet another layer of complexity to this already baffling system. The planet's location in its galaxy adds another dimension to the mystery. It orbits within a relatively quiet region, far from supernova-prone stellar clusters and away from dense molecular clouds. This isolation could have allowed it to remain undisturbed for billions of years, avoiding catastrophic events that might have destroyed or altered it. Yet such isolation is also unusual for planets with its characteristics. Many form in more active regions and later migrate. If this one has always been here, it would suggest a remarkable stability in its galactic environment, perhaps even shielding it from cosmic radiation levels that might otherwise strip atmospheres and sterilize surfaces. In terms of habitability, such a safe neighborhood could be a rare cosmic luxury, making this planet not just strange, but extraordinarily lucky in its placement among the stars. Some researchers have speculated that this planet might be a relic world, a planetary body that has survived from a much earlier era of the galaxy, carrying chemical and structural signatures from a time when conditions were vastly different. If so, studying it could be like opening a time capsule from billions of years ago. Relic worlds can preserve minerals, isotopes, and atmospheric compositions that have long vanished from more active planets. These preserved features could tell us about the early chemical soup from which later planetary systems emerged. For instance, certain ratios of heavy to light elements might reveal whether the material that formed it came from a supernova, a neutron star merger, or some other cataclysmic event. In that sense, this planet may be more than a curiosity. It could be a living record of the galaxy's formative years, quietly orbiting its star while civilizations rise and fall light years away. Communication about this planet within the scientific community has shifted from cautious curiosity to deep collaboration. International telescope networks now coordinate schedules specifically to observe it, ensuring that every transit and spectral reading is captured. This global effort is reminiscent of how astronomers worked together to image a black hole for the first time. Data from different wavelengths and instruments are combined into shared models, with teams across continents debating every anomaly. This kind of collaboration not only accelerates discovery, but also democratizes it, allowing smaller observatories and even advanced amateurs to contribute. As a result, the planet has become a shared project, a kind of collective puzzle that the global scientific community is determined to solve together. There's an emotional dimension to this mystery as well. For many scientists, the act of studying a planet like this is not just about data, it's about wonder. In a universe governed by laws we've spent centuries decoding, it's rare to find something that resists easy classification. This planet does exactly that, standing as a reminder that the cosmos still holds secrets far beyond our grasp. Each observation is a small act of humility, acknowledging that for all our progress, we are still explorers on the shore of an infinite ocean. In the calm darkness of a remote observatory, staring at the faint flicker of its transit, a scientist might feel something deeper than curiosity, a quiet awe of the improbable beauty of a world that by all rights should not be there at all. Speculation about potential missions to this planet is growing. While it lies far beyond our current reach, concepts for future probes, perhaps propelled by light sails or advanced fusion drives, are already being discussed. Such a mission would take decades or centuries, but the reward could be unprecedented: direct images of its surface, atmospheric samples, and a close look at its geology. A probe might even carry autonomous laboratories capable of conducting in situ analysis, freeing future scientists from relying solely on distant observations. These missions, though purely hypothetical for now, serve as a reminder that our curiosity has no boundaries. We may not visit in our lifetimes, but humanity's story is long, and the drive to reach such places is not easily extinguished. For now, the planet remains a point of light in our telescopes, distant, mysterious, and profoundly silent. Its existence challenges models, inspires collaboration, and fuels dreams for exploration. Whether it turns out to be a relic world, a migration survivor, or something entirely unexpected, it has already achieved something rare. It has expanded the horizon of our imagination. In that sense, the truth about the planet may be less important than the questions it forces us to ask, and perhaps that is its greatest gift. Not the answers it might someday give, but the reminder that the universe is still vast enough to surprise us even when we think we understand it. When astronomers attempt to model this planet's internal structure, they face an unusual set of constraints. Its density, derived from mass and radius measurements, does not match common planetary types. It is too dense for a gas giant, but too large for a typical rocky planet. This mismatch suggests an exotic interior, perhaps a massive iron-rich core enveloped by a thin but persistent layer of volatiles, or a combination of silicates, and metals not yet found in any meteorite samples on Earth. Some theories even suggest it could be the stripped core of a former gas giant, left bare after its outer atmosphere was blown away by a cataclysmic event. If true, that would mean this planet has survived something truly extraordinary, the kind of event that would annihilate most worlds. Understanding this structure could help scientists reframe how planets form and evolve, particularly in extreme stellar environments where stability is far from guaranteed. Climate models for this planet present another layer of fascination. While it appears to orbit within the habitable zone, the term habitable does not guarantee Earth-like conditions. Its atmospheric composition, cloud cover, and albedo, the reflectivity of its surface, or clouds, could lead to climates ranging from a frozen desert to a greenhouse world. Simulations suggest that if its atmosphere contains even modest levels of greenhouse gases, surface temperatures could remain surprisingly mild despite fluctuations in the star's brightness. Alternatively, high cloud coverage could reflect enough light to keep the planet cooler than expected, resulting in ice-covered oceans and a climate locked in glacial stasis. The reality could be somewhere in between, producing complex and dynamic weather patterns that are unlike anything we know. This balance or imbalance would be critical to understanding whether any form of life could persist there. The possibility of plate tectonics on this world is particularly intriguing. On Earth, the movement of tectonic plates recycles carbon, regulates climate, and drives the creation of diverse habitats. Whether this planet has similar processes depends on factors such as internal heat, mantle viscosity, and crustal composition. Indirect evidence, such as variable volcanic gas signatures detected in the atmosphere, hints at some form of geologic activity. If confirmed, it could mean this planet maintains an active carbon cycle, potentially supporting long-term climate stability, but it's equally possible that it has a stagnant lid system where the crust remains largely immobile, trapping heat below and leading to massive, infrequent volcanic events. In such a case, life, if it exists, would have to adapt to long periods of calm punctuated by catastrophic upheaval. Astronomers are also investigating whether this planet could have rings. While rings are most famously associated with Saturn, they can form around planets of various sizes under the right conditions. If this planet has a strong gravitational field and an active history of capturing debris, it might host a ring system far denser and more dramatic than any seen in our solar system. Such rings could be remnants of a shattered moon, a captured asteroid swarm, or material pulled from the planet itself during ancient collisions. Observationally, rings could explain certain oddities in the planet's light curve during transits, such as slight asymmetries or dips that don't align perfectly with the planet's orbital path. If confirmed, a massive ring system would not only make the planet visually stunning, but also hint at a violent past. One of the stranger ideas put forward is that the planet's composition could be partially crystalline. Deep in the interiors of massive worlds, pressures can compress elements into exotic forms, including crystalline structures of carbon or silicates. If this planet's mantle contains significant amounts of such materials, its seismic and thermal properties could differ dramatically from typical rocky world. In extreme cases, these crystalline structures could be so vast and pure that they would refract seismic waves in unusual ways, possibly even affecting the planet's magnetic field generation. While the notion of a diamond planet is often sensationalized in popular media, the physics behind such possibilities is sound. If this planet truly harbors crystalline layers, they could offer new insights into the behavior of matter under extreme pressures, conditions that cannot be replicated easily on Earth. Studying the planet's orbital stability offers another window into its history. If its path around the star is unusually circular, it might suggest a long period without significant gravitational disturbances, rare for a planet of its type. On the other hand, a slightly elliptical orbit could hint at past interactions with other massive bodies, possibly sending it inward or outward before it settled into its current position. Precision measurements of its orbital parameters over many years could reveal subtle changes, perhaps caused by unseen planets or even passing stars. These slow drifts, imperceptible on human timescales, can tell astronomers about the broader architecture of the system and whether it remains stable enough for life to take hold. Some researchers have even speculated about subsurface oceans. On icy moons like Europa and Enceladus, tidal heating from a host planet keeps vast oceans liquid beneath frozen shells. If this planet has a strong tidal relationship with a large moon, or if its internal heat flow is high, a similar situation could occur here. Subsurface oceans are compelling because they offer protection from radiation and stable conditions for potential microbial life. The challenge is that such oceans would be invisible to direct observation. Instead, scientists would have to infer their presence through indirect signs, such as slight variations in the planet's gravitational field or unexpected atmospheric gas emissions from cryovolcanic activity. The planet's role in its own solar system is also a point of study. Large planets can act as gravitational shepherds, influencing the orbits of smaller bodies and sometimes protecting inner worlds from excessive asteroid impact. If this planet's gravity deflects or captures dangerous debris, it could serve as a shield for other planets closer to the star, much like Jupiter does for Earth. Alternatively, if it has a more chaotic gravitational influence, it could destabilize the system, sending smaller bodies careening inward or outward. Understanding this role is crucial because it connects the fate of this planet with the broader destiny of its entire system. A lesser discussed aspect is the cultural impact of its discovery. Throughout history, celestial discoveries have influenced art, philosophy, and even politics. The planet shouldn't exist status has already sparked a wave of public fascination, with science communicators using it as a symbol of the universe's unpredictability. In classrooms, it challenges students to question assumptions. In literature, it becomes a metaphor for resilience against impossible odds. This blending of science and culture underscores how astronomical phenomena can ripple far beyond academic circles, shaping the way we see ourselves in the cosmos. Finally, the question arises, could there be more planets like this, hidden in the vastness of the galaxy? The discovery of even one suggests that our classification systems may be incomplete, perhaps biased by the limitations of our detection methods. Future telescopes, with sharper resolution and broader spectrums, could reveal dozens, maybe hundreds of similarly puzzling worlds. Each new find would chip away at our understanding of planetary formation, forcing us to rewrite models again and again. And in that ongoing revision, this particular planet will always be remembered as the one that opened the door, reminding us that the universe is not bound by the patterns we expect, but by the laws it has always followed, waiting for us to uncover them. The search for additional planets in this system has taken on a new urgency. If this impossible world formed here, it might not be alone in defying expectations. Astronomers use transit timing variations, subtle shifts in the planet's orbital period, to infer the gravitational pull of potential neighbors. Any detected variations could hint at another massive world lurking in the shadows, possibly the culprit responsible for this planet's unusual mass or orbit. High-resolution spectrographs, meanwhile, search for wobbles in the host star's light that betray unseen companions. Even if other planets are discovered, none may match the peculiar qualities of the original. Yet their presence could explain aspects of its past, from violent migrations to orbital realignment. In this sense, the planet's mystery is not isolated. It's part of a deeper systemic puzzle where each body's movements are woven into a gravitational tapestry millions of years in the making. In the realm of exoplanetary research, false positives are an ever-present concern. Could the planet be a misinterpretation of the data? This question haunts careful scientists who remember times when stellar spots, binary companions, or instrumental errors created illusions of planets that didn't exist. The research team behind this discovery has reanalyzed their data with extreme caution. They've cross-referenced transit observations with radial velocity measurements, checked for background stars that might distort the signal, and ruled out multiple alternative explanations. The result? A near unshakable confidence that this world is real. Its signature appears across different data sets and detection methods, each one telling the same story: a massive, dense, and utterly baffling object moving in a perfectly timed rhythm around its star. The certainty is a relief, but it also deepens the enigma. If the planet is not an observational error, then the universe truly has presented something unprecedented. To understand the planet's possible origins, scientists have turned to computer simulations that replay billions of years of cosmic history in fast forward. In some scenarios, the planet begins life as a gas giant far from its star, only to be nudged inward by gravitational encounters. In others, it forms closer in but experiences massive collisions that strip away its outer layers. A particularly dramatic simulation shows it being captured entirely, a rogue planet drifting through interstellar space until trapped by the star's gravity. Each scenario has strengths and weaknesses, fitting some observations while contradicting others. What they all share is a sense of cosmic violence, of worlds colliding and being reshaped in ways that challenge the idea of a calm, orderly universe. The simulations make one thing clear: this planet's current form is likely the product of chaos, survival, and chance. The planet's day length, its rotation period, is another source of intrigue. Rapid rotation could flatten its shape, creating an equatorial bulge, while slow rotation might allow extreme temperature differences between its day and night sides. Observations suggest a rotation that is neither too fast nor too slow, a middle ground that hints at a long-term balance between tidal forces and internal dynamics. This stability, however, may be deceptive. If the planet once rotated faster, tidal locking with its star could slowly be drawing it toward a future where one hemisphere bakes in eternal daylight and the other freezes in endless night. For now, its day-night cycle allows for global circulation of heat, potentially moderating climates and creating conditions, however fleeting, that could be more favorable to life. What about life itself? The atmosphere, if it exists in a stable form, could hold clues. The search for biosignatures, chemical imbalances suggestive of biological activity, is ongoing. Oxygen paired with methane, for example, would be hard to explain without some form of life. Yet researchers remain cautious. Abiotic processes can mimic biological signals, and without direct sampling, any claim would be provisional. Still, the prospect is tantalizing. Life here, if it exists, might look nothing like Earth. It could be based on exotic chemistries, adapted to pressures, temperatures, and radiation levels that would sterilize most known organisms. It could exist underground, in deep oceans, or floating in the upper atmosphere. If confirmed, such life would revolutionize biology, proving that evolution can flourish in places once thought inhospitable. Cultural interpretations of the planet have begun to emerge across human society. Science fiction authors imagine it as a refuge for humanity's distant descendants, a world where civilization thrives against astronomical odds. Artists depict it bathed in surreal colors, its skies streaked with light from its unusual atmosphere or nearby debris rings. Even musicians have composed works inspired by its discovery, blending cosmic soundscapes with rhythmic pulses meant to mimic its orbital period. This blending of science and art reinforces the planet's role as more than just a subject of research. It has become a symbol of persistence and mystery, a reminder that reality often exceeds imagination. For astronomers, this public fascination is both a gift and a challenge, a motivation to learn more, but also a weight of expectation to deliver definitive answers. One of the more speculative ideas about this world involves its potential as a stepping stone for interstellar exploration. If humanity develops the ability to travel to other star systems, worlds like this, massive, stable, and rich in resources, could serve as outposts or way stations. Its unusual composition might offer materials rare or absent in the solar system, fueling further journeys into the galaxy. However, this vision depends on factors that remain unknown: surface accessibility, gravitational challenges, and resource extraction feasibility. For now, such ideas remain in the realm of theoretical future planning, but they reflect a broader truth that strange discoveries often inspire dreams far beyond the immediate science. The planet's magnetic field, if it exists, could be a crucial piece of the puzzle. A strong magnetic field would shield its surface from stellar radiation, improving the odds for habitability. Detecting such a field across light years is difficult, but not impossible. Astronomers look for signs in the planet's radio emissions, which could be influenced by interactions between its magnetic field and stellar winds. Early data hints at periodic signals that might fit this pattern, but confirmation requires more sensitive instruments. If proven, it would not only inform models of the planet's interior, but also elevate it as a potential candidate for life-supporting environments. Another mystery lies in its apparent albedo. Observations suggest that the planet reflects far more or far less light than models predict, depending on the wavelength observed. This discrepancy could mean its surface or atmosphere contains unusual materials, metallic frost, silica clouds, or even photochemically produced hazes that scatter light in unexpected ways. Such features could alter the planet's temperature balance and even its visibility to telescopes. In the broader context, studying these reflective properties helps scientists refine methods for detecting and characterizing other distant worlds where small variations in light can hold massive implications. As the research deepens, one conclusion becomes clear. This planet challenges the very language we use to describe planets. Our categories, rocky, gaseous, icy, feel insufficient. It occupies a gray area demanding new terminology and new conceptual frameworks. Its discovery reminds us that classification in science is always provisional, a tool for understanding rather than a final truth. As more observations come in, we may find it fits neatly into a new category, or that it remains an outlier, a cosmic exception to every rule. Either way, its legacy is secure. Long after the details of its composition, orbit, and history are understood, it will be remembered as the planet that shouldn't exist, and yet does, silently circling its star, a beacon of cosmic possibility in the vast dark. One avenue of investigation involves studying the planet's orbital stability over astronomical timescales. A planet with such extreme characteristics might be vulnerable to perturbations, subtle gravitational nudges from other planets, the star's own activity, or even passing stars in the galaxy. Computer models simulate its motion forward and backward in time, revealing whether it has always been in its current position or if it migrated here in the past. Interestingly, some simulations show the planet drifting inward over millions of years, while others predict it will slowly spiral outward in the distant future. This instability might one day lead to its ejection from the system entirely, turning it into a rogue planet wandering between the stars. If that happened, its current warmth and light would vanish, plunging it into eternal cold. But for now, it remains balanced, improbably, almost precariously, in a gravitational dance with its star. The chemistry of the planet's atmosphere may hold the clearest fingerprints of its origin. Spectrographs on space telescopes dissect starlight as it passes through the thin veil of gases surrounding the planet during transit. Each chemical leaves a unique pattern of absorption lines, a cosmic barcode. Preliminary results are perplexing. There are strong signals from heavy metals, compounds usually found deep within a planet's core, not floating high in its skies. This suggests the atmosphere may have been polluted by catastrophic impacts, tearing open the planet's crust and sending material into the air. Over time, such debris would settle or escape, meaning we are catching the planet in a rare, transient phase of its evolution. It is like walking into a room moments after an explosion, the debris still suspended, the air still shimmering from the force. Some researchers are exploring whether tidal heating plays a role in the planet's unusual properties. If it once had an eccentric orbit, constant gravitational stretching and relaxing could have generated immense internal heat, reshaping its structure. Even now, if there are undetected moons orbiting it, their combined pull could continue to stir the planet's interior. On Earth's moon, tidal heating is negligible, but on places like Jupiter's moon Io, it drives relentless volcanic activity. If this planet experiences similar forces, its surface, if it has one, could be a restless landscape of molten rivers and erupting plumes. From space, these outbursts might glow faintly in infrared, a heat signature that betrays the turmoil below. Detecting such a signature would require years of precise measurements, but it would be a direct window into the planet's deep heart. The possibility of moons raises further questions. Large moons can act as stabilizers, preventing excessive wobbling in a planet's axis and creating conditions more favorable for life. They can also be worlds in their own right, potentially habitable, even if the planet is not. In our solar system, moons like Europa and Enceladus harbor oceans beneath icy shells, warmed by tidal forces. If a similar moon orbits this strange planet, it could be a hidden gem, a sanctuary of liquid water and chemical richness, orbiting an otherwise hostile world. Unfortunately, detecting moons around distant exoplanets is extremely challenging. Subtle variations in transit timing and light curves are the only clues, and so far, no definitive signals have emerged. But given the planet's history of chaos, the idea of captured or formed moons is far from impossible. Another intriguing aspect is the planet's reflectivity in different seasons, if seasons exist here at all. On Earth, tilting toward or away from the sun changes the amount of light an area receives, creating the cycle of seasons. For this planet, its axial tilt is unknown, but even a slight one could have dramatic effects due to its proximity to its star. An extreme tilt could cause prolonged periods of light and darkness at the poles, altering atmospheric circulation. If there's a thin atmosphere, such seasonal shifts might whip up violent storms or blanket one hemisphere in reflective clouds for months at a time. Detecting these patterns would require years of patient observation, but the payoff would be enormous. Proof that even alien climates can have rhythms, cycles, and perhaps a kind of weathered beauty. Public fascination with the planet has not waned since its discovery. Documentaries explore its physics, podcasts speculate about its history, and online communities share artistic interpretations that blend science with surrealism. Some depict it as a cosmic survivor, a world that endured cataclysm after cataclysm. Others imagine it as a trap, a place that lures explorers with promise but hides lethal conditions beneath its cloud. While these portrayals are fictional, they capture something real: our deep, emotional connection to the unknown. The more we learn about the planet, the more we see our own struggles reflected in it, resilience, adaptation, and mystery. This emotional resonance fuels continued funding and interest, ensuring that the search for answers will continue for decades. The planet's gravity is another source of curiosity. Based on its mass and radius, surface gravity might be several times stronger than Earth. Such a force would shape everything about the environment, from the density of the atmosphere to the height of possible mountains. In extreme gravity, a human could barely walk, and the tallest peaks would be much lower, crushed under their own weight. Oceans, if they exist, would be deeper but calmer, their waves suppressed by the force. Even the atmosphere would behave differently, potentially layering in dense strata that trap heat. Such conditions would make visiting the planet extraordinarily difficult, but they also create a unique laboratory for physics. A world where the familiar rules of motion, pressure, and erosion are bent by sheer mass. If the planet has a solid surface, its geology might reveal its entire history. Impact craters could show how often it's been struck by asteroids or comets, while patterns of volcanism might reveal whether it has active tectonics. Plate tectonics, in particular, would be a surprise. It's rare even among large rocky planets. But if present, it could mean that the planet recycles its crust, renewing its surface and maintaining geological activity for billions of years. This constant reshaping could erase signs of older impacts, making the planet appear younger than it is. A geologically active surface could also vent gases into the atmosphere, influencing climate and habitability. The challenge is that we can't directly photograph such details from light years away. We have to read them indirectly in spectral lines and brightness shifts. The star it orbits also plays a key role in its story. Stars evolve, changing in brightness and temperature over time. If the star was dimmer in the past, the planet's current position might once have been frigid, only becoming warmer as the star aged. Alternatively, if the star flares often, as many small stars do, it could bathe the planet in bursts of radiation, stripping its atmosphere and altering its chemistry. Understanding the star's life history is as important as studying the planet itself. In astronomy, planets and stars are inseparable partners, their fates intertwined. The mystery of this world is also the mystery of its sun, a relationship written in light and gravity. Some scientists suggest that this planet is not unique, only the first of its kind we've been lucky enough to find. If our detection methods improve, we might uncover an entire class of impossible planets scattered across the galaxy. Each could challenge different aspects of planetary science, forcing us to rewrite models again and again. This thought excites astronomers because it means the universe still holds surprises that can reshape entire fields. For now, though, this planet remains alone in its category, a solitary flag planted in the uncharted territory of the cosmos. And perhaps that is fitting. Its very existence is a reminder that the unknown is not a distant frontier. It's right here, orbiting quietly, waiting for us to notice. One area of active research is whether the planet could host a magnetic field. On Earth, our magnetic field shields us from harmful solar radiation, guiding charged particles safely toward the poles where they create auroras. Without such protection, a planet's atmosphere can be eroded by stellar winds over millions of years. Determining if this planet has a magnetic field is tricky. We can't just send a probe to measure it directly. Instead, astronomers look for signs like auroral emissions in the planet's upper atmosphere detected in specific wavelengths of light. If such emissions exist, they would be an unmistakable signature of magnetic shielding. However, the strength and stability of that field would depend on the planet's internal composition. If its core is molten and conductive, swirling convection could generate a powerful dynamo. If not, The planet may be fully exposed to its star's radiation, shaping its destiny in ways we are only beginning to understand. From a cosmic timescale, we might be catching the planet in a fleeting stage of its life. Planets evolve, and some phases last only a fraction of their total existence. For example, a hot, inflated atmosphere may slowly contract and cool as a planet loses heat to space. Over eons, volatile compounds might escape entirely, leaving behind a barren, rocky core. If this planet truly shouldn't exist, perhaps it won't for much longer, not in its current form. Studying such transient stages is invaluable because they act as natural laboratories, showing us processes that shaped planets billions of years ago when our own solar system was young. This makes the planet a time capsule, preserving conditions that may have once been common but are now rare. In the grand arc of the galaxy, we might have stumbled upon a world in the middle of becoming something entirely different. There's also the matter of how it formed in the first place. Most planets form from a disk of dust and gas surrounding a newborn star, with their position and size determined by the distribution of material. Yet this planet's size, density, and orbit don't match what models predict. One theory suggests it formed far from its star and migrated inward, pulled by gravitational interactions with other giant planets. Another posits it formed in place but was heavily bombarded by massive asteroids early in its history, drastically altering its structure. Both scenarios require extreme events, the kind that might only occur rarely in the galaxy. If migration was the cause, the journey inward would have been violent, with the planet possibly swallowing smaller worlds along the way. That could explain its unusual density, as each collision added more mass to its core. Migration theories lead to fascinating implications about the rest of the system. If this planet moved inward, where did the other planets go? Some might have been ejected entirely, becoming rogue wanderers in interstellar space. Others might still be there in distant orbits too wide for our telescopes to detect. Yet, this paints the picture of a planetary system in chaos, its history written in scattered debris and altered orbits. In such a system, stability is temporary. Even the current arrangement might shift again over millions of years. This possibility makes the planet not just an oddity, but a survivor of cosmic upheaval, and it hints that stability, like life, might be more fragile in the galaxy than we once thought. If the planet has rings, they could offer more clues. Rings are usually made of ice, dust, or rocky debris, and can be remnants of moons torn apart by tidal forces. The brightness, thickness, and composition of such rings can reveal their age and origin. Saturn's rings, for example, are relatively young in astronomical terms, perhaps only 100 million years old. If this planet has similar structures, their presence could indicate recent destruction event. Observing rings from light years away is challenging, but subtle dips in a star's light during transit can hint at their existence. If found, they would add yet another layer to the planet's already complex story, transforming it from an enigma into a cosmic spectacle. The search for potential life here is more about possibility than probability. The extreme conditions make it unlikely for life as we know it to thrive on the planet's surface. However, if it has subsurface oceans beneath an icy crust, microbial life could exist in protected environments. This mirrors the situation with moons like Europa and Enceladus in our own system. Life in such places might be entirely cut off from the surface, surviving on chemical energy rather than sunlight. Detecting such hidden biospheres from afar is nearly impossible with our current technology, but their theoretical existence is enough to keep astrobiologists interested. Even if life here is unlikely, studying the boundaries of habitability sharpens our understanding of where and how to look elsewhere. One rarely discussed angle is the planet's potential impact on its star. While we think of stars as dominating their planets, the reverse can also happen, especially with massive worlds close to their suns. The gravitational pull of the planet can subtly distort the star's shape and influence its activity cycles. In some cases, this interaction can even enhance stellar flaring or magnetic activity. If that's happening here, the planet is not just a passive object, but an active participant in shaping the behavior of its star. It becomes part of a feedback loop where the star changes the planet and the planet changes the star, a dynamic relationship that challenges the notion of planets as mere bystanders. In the realm of public imagination, some speculate that such a planet could one day be visited not for colonization, but as a scientific pilgrimage. Future probes or crewed missions could skim its atmosphere, deploy landers, or drop deep penetrating probes into its crust. The data from such missions would be unparalleled, giving us direct answers to questions that currently live only in equations and telescope data. However, the engineering challenges are enormous. Surviving the descent into such gravity with potential storms and intense radiation would require technology far beyond today's capabilities. Still, the idea persists because the reward would be not just knowledge of one planet, but insights into the very processes that shape worlds across the universe. The planet's greatest mystery may be that it defies easy categorization. We like to place planets into neat groups: gas giants, ice giants, rocky terrestrials, super-Earth. But this world overlaps categories, blurring boundaries we thought were clear. Such anomalies are valuable precisely because they resist classification. They force us to refine our definitions and expand our models. In that sense, the planet is not a problem to be solved, but a teacher. It reminds us that the universe is not obligated to match our expectations, and that reality often has more imagination than we do. Each new piece of data deepens the mystery instead of resolving it, ensuring that this planet will remain a focus of curiosity for generations of scientists to come. In the end, the planet that shouldn't exist has become more than just a line in a catalog of exoplanets. It is a symbol of the unknown, a reminder that the universe still has the capacity to surprise us in profound ways. Long after the first excitement fades, its study will continue, driven by the simple human desire to understand. Perhaps decades from now, we will know exactly how it formed, why it has the properties it does, and what its future holds. Or perhaps we will uncover even deeper mysteries that make the current questions seem simple by comparison. Either way, this planet will have done what all great discoveries do. It will have expanded the boundaries of our knowledge, and in doing so, expanded the boundaries of ourselves.